What's up, everybody? I hope you're having a good Monday. Hope that you have enjoyed the 24th so far. It's been pretty good for me. Um, what we're going to do today is go ahead and crack into some biochemistry. We've got class today, class Wednesday. We'll be talking about lipids, we'll be talking about membranes. And then we'll have our next exam 1 week from Wednesday. A week from today, we'll spend that time um, reviewing in advance of the exam on Wednesday. I have posted your practice exam, so that is up. I can't remember if I sent out a link announcing it. If I haven't, I will do that. I will check on that later today. Um, but that's available. I've also, at the same time, I wrote the exam. Um, so I wanted to make those things kind of aligned with one another. Um, and so that's where we are. Now, at this point in time, we're talking about lipids, and I got to be honest with you, lipids are one of my favorite topics to discuss, in part because they're a little bit neglected. And what I mean by that is there's a tendency in like a first semester biochemistry class and even a second semester, like a metabolism class, to get all jacked up about sugars. Sugars are interesting. Proteins are interesting. Yes, yes, yes. I'm not going to argue at that point, but I think that lipids are very important because they do a lot of different things. In addition to that, from a metabolic standpoint, um, could anyone add to the chat which of the three following macromolecules um, do you get the most caloric value from? Lipid, proteins, or sugars? It's a lipid. Lipids provide the most caloric value, which is one of the reasons that I think lots of people are very enticed and lots of people lean towards a high fat or a fat rich diet because you can eat a little bit of a saturated fat and get a huge sum of energy. So there's definitely like value in that. Now, we are going to talk about lipids. We're going to talk today about a couple of different things related to them. I want you to today walk away with an understanding of the structure of a fatty acid. I also want you to, and I still am working on this, and I think the first time that I learned about lipids was around 20 years ago. Um, and I still kind of struggle with this because I have a bad habit of um, I have a bad habit of using terms interchangeably when they should not be used interchangeably. It's kind of inappropriate to use them interchangeably. For example, there are times when I will have to correct myself and say, no, I'm talking about a fatty acid, not lipids. Because think about lipids as a more broad, overarching term. Now, underneath lipids, there are a couple of other terms that we're going to get into today, and we're going to get into the structure of those. Now, for the most part, the structures that we'll look at have a little bit of a formula and a little bit of a pattern to them, um, but there are some tweaks to it. Now, with that in mind, I want to give you a definition. Lipids are none other than substances of biological origin that are soluble in organic solvents. Very unique. Why is that unique? Could anyone add to the chat why that or what that sentence, what about that sentence or statement is unique? And there's actually a couple of different directions that you can go with that. And I know I have a bad habit of asking like very leading questions that I know the answer, that I know what I'm looking for. And I apologize for that. But what I'm looking for here, okay, they can dissolve in a membrane. Yeah. What I'm looking for here with, hey, this is really odd, is organic solvents. And I say that just because when you think about a cell, if you think about like the cytosol or the cytoplasm, the interior of a cell, well, that's an aqueous environment. That's a water soluble environment. That's not an organic environment. So the solvent within the cytosol is water. It's not hexane, it's not decane or any organic solvent. So lipids are super unique because of that because of that factor and because of that kind of property. Now, lipids do three major things. I'm going to switch to my highlighter for this. The first thing is that they form a bilayer. And we're going to have some new terminology on Wednesday that I want you to feel comfortable using. And maybe you've heard some of these leaflet, or you've heard this term leaflet. So we're going to talk about the inner and outer leaflets. But lipids in form of a bilayer are essential components of biological membranes. If you've ever heard the term lipid bilayer, that's an important term that we need to know for membranes. Second up is that lipids containing hydrocarbon side chains serve as tremendous energy stores. Now, this is the point where, well, if you think about energy storage or a relationship between caloric value and a nutrient, um, lipids with hydrocarbon side chains are where that's coming from. And then last but not least, and I think that this is like super important, is many intra and intercellular signaling events. So that means basically what's happening within the confines of a cell, but also between different cells, involve lipid molecules. Okay, so I would go as far as to say that signaling events are related to lipids, and lipid related molecules or lipid molecules um, are pretty important for signaling. So basically, if you think about one cell's response to sensing a hormone, like we'll just go with glucagon, um, the interior response to that is going to be triggered by a lipid molecule. And then there are also molecules that are produced like in responses to pathogens, like, hey, I'm under attack. That communication outward can also be done by lipid molecules. Now, when it comes to lipid classification, our five most important lipid classes are first and foremost fatty acids. Second are triacylglycerols. Third, glycerophospholipids. Fourth, one of my favorite all-time science words, sphingolipids. And last but not least are steroids. These are the five classes that we're going to talk about the most. And we're going to go through today's lecture kind of in that sequence. We'll end with a discussion of steroids. But up until then, we're going to be kind of parsing this information out. Now, this, the way that all this information kind of like congeals or mixes together in my head is these first three items, they're very closely connected. And, you could maybe even make space for that fourth one, those sphingolipids. But these first three are really closely connected in my head just because fatty acids are base molecules and we're going to build out from there. Um, Now, one thing that's important about lipids is that they, unlike most of our other biological macromolecules, they do not form polymers. And what I mean by that is you're not going to take one lipid and link it to another, that links to another, that links to another kind of, and this is a nice law word, in perpetuity. It's not going to continue on for forever. The first fatty acid. So basically here is kind of a nice foundation for information that I'd like you to know. Um, they make up lipid bilayers and are major components of biological membranes. They're energy storage and they're for signaling. And then what kind of stands out about them is unlike our other biological macromolecules, they don't form polymers. That's not to say that be assembled into something larger than the individual components, but they don't link up. They don't like with you know, glycogen. Glycogen is a polymer. You have nothing similar to that in a lipid that can be, 600 subunits long or 600 individual pieces long. Now, can I get a Y in the chat if you're good with that? Sweet. Okay. Now, this next thing that I want you to do, I've got this next slide as a blank slide because what I'm going to do is I'm going to show you the basic structure for a lipid. And sorry, what did I say that I do that's very inappropriate? I use the terms lipid and fatty acid interchangeably, and lo and behold, I just did. I'm going to show you a fatty acid. Now, when you hear fatty acid, the first thing that I want you to hear is acid. And whenever you hear fatty acid, I want you to think, okay, what is that acid? It is none other than a carboxylic acid. Now, carboxylic acid is going to be the carboxylate ion at room temperature and at a neutral pH. I don't know why I said temperature before I said pH because temperature has really little to no dependence on it. So this carboxylate ion right there is the acid component of a fatty acid. Now, the rest of it is a hydrocarbon chain. Now, with that in mind, what I'm going to draw from here, this R group, that's the important part about a fatty acid. I've got some slides that follow that basically are going to fill in the same information, but I feel like it's helpful to kind of deliberately work through this. If I were to say C18, does anyone have and I said, hey, this C18 is super significant to a fatty acid. Could anyone add to the chat what they think the significance of that is? With their knowledge of the periodic table and the letter C, what do you think the C18 stands for? Okay. 18th carbon, the carboxylate ion. Okay. Megan, nail, hammer, head. Done. There are 18 carbons in this fatty acid. Kevin, absolutely right. Lucia, 18 carbons. Lauren, you as well. We have 18 carbons. So if I were to say something like this, C12, I said, oh, this is just as significant. I think the rest of y'all or everyone would say there's probably 12 carbons in that fatty acid. And you'd be absolutely right. Now, the next thing that is important for fatty acids is a colon that follows that number. Now, that colon can either be followed by a 0 or a whole number or whole number. For example, 1 or C12 colon 2. Now, what's significant about that 1 or that 2 or that 0 is this tells you, and I'll give you I'll give you some terminology, and that is going to be I'll just say the number of double bonds. Now, a fair question whenever you look at a fatty acid and you see that notation C12 colon 1, C12 colon 0 or 2, do you think, and I'd like a response in the chat for a Y or an N, do you think that this double bond that I've just drawn an arrow to, do you think that is a part of the count? I like it. No, you're absolutely right. It is not. And a good kind of idea for why that is, or a good sign of what that means is no, it's not, is because if you look at C18 colon 0, well, every fatty acid has to have this carboxylate ion. So it has to have at least that double bond that's a part of the carboxylate ion. This question right here, this number of double bonds is in reference to the number of double bonds that are in the hydrocarbon side chain. Now, with that, what I'd like to do is I'm going to go ahead and draw. Let's go with, just because I sometimes lose my drawing abilities as the hydrocarbon chain gets progressively longer and longer, I'm going to go ahead and draw this. So I've got 3 carbons, 4. I'm going to draw 12:1 and 12:2. Well, no, I'm going to start with 12:1. Okay, so I've got 4 carbons, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've got 12 carbons there, and H2, H2, H2. Every single one of these carbons that I'm drawing is going to have, well, nothing but hydrogens. So every single one of these is going to have nothing but single bonds. What I've drawn right here is C12 colon 0. Now, after that, Joel will come on. And I'm going to toggle over to see about how I can take a gander at this drawing if it pops up. Let's see what I can do. I was hoping that I could get to a point where I could copy and paste the whole thing, but that doesn't appear to be the case. Okay, so yeah, no dice. Okay, so there's our C12 colon 0. Now, if you want, go ahead and take a snapshot of that in your head. And let's go ahead. And now what we're going to do is we're going to add a wrinkle to it. And some of y'all might be thinking, oh, well, why don't you just draw the skeletal structure? I have no qualms with drawing the skeletal structure. I got to be honest, though, I'm just kind of a square, and I like to draw every hydrogen, every carbon. Okay, so 2, 4, 6, 8, 10, 12. Okay. Now, just for the sake of time and drawing this molecule, I hope everyone will grant me that. Just imagine that this has nothing but, no, I'm not going to do that. H2. I'm going to do the right thing. And let's go here. H2, 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 H2. Okay. So this C12 colon 0, this is considered to be a saturated fatty acid. Now, if you know anyone who's like a nutrition, let's see, I screw up the terminology here as well. A dietitian. Dietitian, I think, is the correct actual like credentialed term, whereas a nutritionist is the Instagram credentialed term that is not associated with any sort of professional credentials. So this is a saturated fatty acid. So if anyone's ever given you nutrition advice about, oh, make sure that you reduce the number of saturated fatty acids or something like that, this is what they're talking about, reducing this number of saturated fatty acids. Now down here, I've got C12 colon 1. This is a monounsaturated fatty acid, meaning that it has one double bond. When you look at this and you say, okay, well, I've got that double bond in the middle. I've got this notation C12 colon 1. What is the difference between what I see right there and I'm going to go ahead and draw you a different configuration of it. Let's put the double bond right here. Are those different fatty acids? This is a little bit less than 10% of your daily caloric intake. Should be saturated fatty acids. I think that, okay, awesome. Monounsaturated fatty acids, what I just showed was I moved the double bond from where I had this star to now where I have, I'm going to go ahead and put a check mark. is there any difference to them? And that's a little bit of a complicated question. It's a little bit of a um, not not a question, not intended to be a trick question, but the answer is yes, there is some difference to them. Now, in terms of their physical properties, the difference is going to be very marginal. Melting points might vary by a handful of degrees or something like that. And handful of, let me rephrase that, like a handful of a tenth of a degree or something like that. But whenever we talk about fatty acids, we actually do need to keep track of where the double bonds are. If anyone's ever heard of omega-3 fatty acids, for example, you should eat lots of salmon or avocados because that's going to give you your omega-3 fatty acids, fish oils. Ingest those because those are good at combating inflammation. Now, what that relates to is the placement of a double bond. So this right here, the way that I've drawn this fatty acid, C12 colon 1, I'm going to erase that check mark and I'm going to erase that star. This right here can be denoted in two different ways. One way is the omega numbering scheme. And the omega numbering scheme uses the omega symbol or the single letter n, or the lowercase letter n. And whenever you do that, what you will do is you'll say omega minus 3, n minus 3. Okay. Now, what I'd like you guys to do is I'll tell you right now that this fatty acid that I've drawn, the one, this C12 colon 1, is indeed an omega-3 fatty acid. Now, with that knowledge, I'm going to give you two options. And I'd like you to add to the chat first your vote for which carbon is the highest priority. Does everyone see the A and the B that I've written by my two terminal carbons? Okay, so which is the highest priority and therefore by our organic numbering gets number 1? Add to the chat, A or B. Awesome. I'm seeing nothing but A's, and you're absolutely right. So that is our carboxylate ion is carbon number 1. Great job. Okay. Now, I told you that this was an omega-3 fatty acid. I stand by that. And now I'm going to put my A. I got my A and my B. When you're numbering an omega fatty acid, add to the chat. Are you starting from A, your highest priority carbon, or B? Okay. I'm seeing nothing but B, and that's fantastic. You're absolutely right. One way that I always kind of think about that is omega, terminal, or end, like the Charlton Heston movie that I Am Legend was based on. Omega Man, the last man was the premise of the movie. Okay, so B is where we're coming from. Our methyl carbon is what we're using as our numbering scheme for the omega system. Now, I'm going to go ahead and put a box around this. And now what I want to do is I want to also give you the delta numbering scheme. And actually, let's go ahead and I would like you guys to add to the chat the number that you think if I'm going to denote this fatty acid, I'm going to say C12 colon 1 delta, and then I'm going to include a number. Tell me what number you would include, and I'll give you a little bit of a hint. The delta and the omega system come from different backgrounds, and I'll elaborate on that in just a second. 9. Okay, so man, this is great. You guys don't. I'm not saying this as like Joel's pity party, but you guys don't need me this evening. So wonderful. Good job. You're spot on. This would be delta 9. So if you were to look at C12 colon 1 and you were to speak to a chemist, that hardcore chemist is going to say, oh, this is delta 9. And you're going to say, okay, cool. And then if you're to speak to someone who has a background in like molecular nutrition, they're going to say this is omega minus 3 or N minus 3. The omega and N are pretty interchangeable. Okay. Can I get a Y in the chat if, yeah, I'm good with that. Great job, everyone. Great job. Okay, so what I've got in the next few slides are basically elaborating on those points and kind of providing more detail. I like to build this out and I like to have you guys kind of like watch as we're constructing one. Now, with that in mind, this is a total of 4 different fatty acids shown on the right here. They all have different names. Stearic acid, oleic acid, linoleic acid, and then alpha-linolenic acid. These are all fatty acids. Stearic acid is the name for a 18 carbon long saturated fatty acid. Oleic acid is a monounsaturated fatty acid. Linoleic and alpha-linolenic acid are both polyunsaturated fatty acids. Polyunsaturated meaning it has 2 or more double bonds. Now, here's kind of that background. Another little detail is that the predominant length of fatty acid residues, and these would be fatty acid residues, are between 16 and 18 carbons long. Saturated versus unsaturated fatty acids. The nomenclature, talked about that. The number of carbons followed by the number of double bonds. What we looked at on the previous slide was a monounsaturated fatty acid. But when you have a polyunsaturated fatty acid, it gets a little bit complicated. Your double bonds, when they're naturally occurring, are going to have the cis configuration. If ever you, I think it's like McDonald's and lots of other restaurants and Oreos will always advertise that they don't have any trans fats in their or foods, or these are not used in, or sorry, they're not fried in anything that produces trans fats. And the significance of that is trans fats are going to be metabolized in a slightly different way. So your double bond configuration and your naturally occurring fatty acids are going to be in the cis configuration. Your first double bond typically is going to be found between carbons number 9 and 10. Now, the important thing there is you've got to think about, well, delta versus omega scheme. This numbering right here, 9 and 10, that's referencing and that's starting from your carboxylate ion, your highest priority carbon. Now, in polyunsaturated fatty acids, the double bonds are not conjugated. What I want you to take away from that is there's always going to be a pattern in your naturally occurring fatty acids. And that pattern is going to be shown right here. What that looks like is and the way that this kind of sticks in my mind is we've got a double bond, a single, followed by a single, followed by a double bond. That's the naturally occurring pattern. When you have a polyunsaturated fatty acid, the naturally occurring fatty acid or the naturally occurring double bond pattern is going to be double, single, single, double. And if you have three double bonds, it's going to look like this. Double, single, single, double, single, single, double. Can you have more than 3 double bonds? Yeah. Can you have fatty acids that are longer than 18 carbons? Absolutely. Now, what I want to stress here, and this is, I like these slides because it gives you these very commonly occurring and relevant fatty acids. But one of the downsides in my mind is if I said, hey, look at this oleic acid, and you were to think about this using the omega scheme and the delta scheme, you would label this C18 colon 1 delta 9. Can I get a Y in the chat if you agree with that statement? Okay. What would your numbering be if you use the omega or the N minus 1 convention? Well, then it would be C18. I am just going to give the numbers N or 18 colon 1 N minus 9. And so if you're fresh to this, if you're new to this, you might look at it and be like, "Oh, well they both are using the number 9, so obviously my numbering starts from the same position." That is kind of a hazard of doing this. Now, with that in mind, linoleic acid, I'm going to label this fatty acid with the delta numbering scheme, 18 colon 2. And when we use the delta numbering scheme, we say where the double bonds begin. So this would be delta 9, comma, 12. If we looked at alpha linolenic acid, it'd be delta 9, 12, and 15. Can I get a Y in the chat if that makes sense? And you're good with that. Trinity, I like it. Okay, great. Now, if we are to look at the omega numbering scheme, 18 colon 2, N minus. Okay, so we've got 1, 2, 3, 4, 5, 6. Omega minus 6, or N minus 6. It's a little bit tricky because you might look at that and say, "Oh, sure, but you've got to include more information." But I'll let you know that this right here is all of the information that you need to talk about alpha linolenic acid, N minus 6. Could anyone provide an explanation or think of an explanation why that's all the information that you would provide? And I know these are kind of longer responses, but N minus 6, that's all that I write. Megan, you're absolutely right. Because we have that set pattern of double, single, single, double. So when you're using the omega or the N numbering scheme, all that you do is identify where one of your double bonds are whenever you have a polyunsaturated fatty acid. So I always kind of think about that as it's almost like a gatekeeper. It's like if you don't know this information, don't bother asking. So that's one of the important things. Can I get a Y in the chat if you follow the difference between the omega and the delta numbering scheme? Okay, great. Awesome. Okay, so then with that, I'm going to jump ahead a couple slides. The next few slides have a more deliberate explanation of the omega and the delta numbering scheme and kind of layers it on there. Um, so there's our fatty acids. Here's our omega carbon atom. This is always a little bit backwards because it takes our fatty acid and flips it. Find out where your carboxylate ion is right there. Now, there we go. One of the important things about saturated versus unsaturated or polyunsaturated fatty acids is how tightly they pack. So if we have saturated fatty acids, those long hydrocarbon chains with nothing but carbons and hydrogens, what are they going to hate? Is they're going to hate being around water. What are they going to love? Being around each other. And I like this figure so there's our model of our two, our monounsaturated fatty acid represented by B and our saturated fatty acid represented by A. Those unsaturated fatty acids, whether they're mono or polyunsaturated fatty acids, they have a little bit of a kink. And whenever that is introduced, it gives a little bit more mobility. Now, this next model that I want to show you guys, looking at model C, specifically looking at C, that is a total of 5 saturated fatty acids. And what I want you to notice about those 5 saturated fatty acids is it's almost like they're, I don't know what a good example is. It's almost like they're crinkle French fries. You just pack 5 of them together and they like fit hand in glove next to one another. That's nothing but saturated fatty acids. If we look at option D, however, that's a mixture of saturated and unsaturated fatty acids. And what do we notice? And I'll just give you a little bit of a space. I always just draw something and say, okay, well, that's approximately on my screen. Let's say that that's an inch and a half. Okay. I'm talking about the x-axis here. This is approximately 1.5 inches wide. And I'm going to start over here and I'm going to draw that same about 1.5 inches. Now, my question is, do I have the same total number of fatty acids packed in those same spaces? I don't. So your saturated fatty acids are super dense. They can pack really well together, which is why, or which is one of the reasons whenever people talk about, you know, intake of saturated versus unsaturated fatty acids, if you're consuming saturated fatty acids, you're getting these densely packed molecules, these densely packed energy-rich compounds, which Abdullah added that it was, I believe that's who it was, approximately 10% of your diet, your daily dietary intake should be limited to um, saturated fatty acids. And you shouldn't really go above that. Um, if you're somebody who runs a marathon every 2 days or something like that. And I know that over the years I've known people who do like CrossFit, so they climb up a fence and then they throw a ladder and they jump over this and that. And they do lots of stuff. They're using that energy from those saturated fatty acids. So whenever they're like, "Oh, I eat nothing but bacon grease and 4 egg yolks," then they are consuming that energy. Their body is using that energy. But that's not everybody. So they're consuming calorically dense nutrients and they're using those calorically dense nutrients or they're using all those calories. So this is one of the differences between your saturated and unsaturated fatty acids and kind of what it looks like on a microscopic level for drawing a connection between, I guess, like macroscopic caloric use. Now, whenever we think about fatty acids, I think that it's important to think about properties, like physical properties of fatty acids. This next slide shows us a table. And I know every time I took a chemistry class, I was like, oh, give me a table because I'm going to memorize that and hope that the exam is nothing but this table. What I want you to know about here is trends. Now, this table right here has a lot of information, and good news is, I think that lots of this information isn't super important for us. This is detailed, it gives us all the information, but what I want you guys to know is I want you to recognize the trends. Now, what are the things that we've kind of been familiarized with and exposed to? Well, we've talked about our carbon skeleton. 12, 0, all the way down to 24, colon, 0. So these are our saturated fatty acids. And if you look at the structure, oh, cool. Yeah, I gotcha. Just adding carbons, increasing our number of carbons. And then if we look at our systemic name, oh, great. They all have systemic names, systematic names. Yeah, systematic, not systemic. Difference. Do I need you to know those systematic names? Do I need you to know these common names? I don't. Are there going to be some points where it might benefit you if you go on to either medical school or PA school or some sort of professional school to know myristic and palmitic acid and maybe even yeah, actually I'll go ahead and include that to stearic acid. Yeah, those are terms that they might be helpful for you, but for this class, I'm not going to stress about that. Now, what I want you to notice about these is there's a trend. I'm going to scribble out the systematic names. I'm going to scribble out the solubility. We don't really need to know the common names. But what do you notice about the melting point of these fatty acids? And just between let's see, the 62 of us, This was something that I always kind of struggled with, and it was helpful for me to put it in context. Um, could somebody add to the chat roughly what room temperature is in degrees Celsius? Great. I love it. About 25. Okay, so um, let's take lauric acid. Lauric acid has a melting point of about 44.2. So this is putting this into context. If I like if you had a hand with a glove on it and I said, "Hey, I got some lauric acid for you." And you're like, "Okay, cool. It's a fatty acid. Gotcha." And I said, "Put your hand out and I'm going to put lauric acid on your hand." Is that lauric acid going to be a solid or a liquid or a gas at room temperature? Solid. Because at 25 degrees, we are below our melting point. So only when we get to about 44 or above will it transition to being a liquid. Okay, so most of your saturated fatty acids, and this is a nice general idea, your saturated fatty acids are going to be, well, they're going to be a solid at room temperature. Okay, now below that, we got this whole other list. We've got palmitoleic acid, oleic, linoleic, alpha linolenic, arachidonic acid, which, man, oh man, if I were musically inclined and wanted to have a metal band, our name would be arachidonic acid. But I haven't reached that point in my life yet. It will happen. Um, and then every band member would be one of the arachidonates, or it could be Joel and the arachidonates, like the Diana Ross and the Supremes. So we'd be a Motown metal band. Okay, so all these fatty acids at the bottom. We've got mono and polyunsaturated fatty acids. Um, let's go with first one right off the top. Palmitoleic acid. Is palmitoleic acid going to be a solid or a liquid at room temperature? Liquid. Yep. Because the melting point being 1 to zero point 0.5 degrees, yeah, 25 degrees is well above that. Now, I like to bring this one up because what we have here is this requires kind of a closer view. Oleic acid and palmitoleic acid. What I want you to notice here is we've got 7 CH2 and 5, and then 7 and 7. Okay, so our double bond is in a slightly different location. So, and we've got a slightly longer fatty acid, 16 and 18 carbons long. What has happened between this one and this one? These are both monounsaturated fatty acid, but the fatty acid got a little bit longer. What happened to our melting point? It went up. Are they both liquids at room temperature? As my relatives in Western Wisconsin would say, you betcha. They're absolutely both liquids at room temperature. But as we increase the number of carbons, what happened to our melting point? And the great thing is, I know most of you guys don't have your camera on, but you still probably did this. You either mouthed, went up, or you motioned up, or you did something to articulate that yes, you know that as the number of carbons increases, so too does the melting point. But then if we go a little bit further, we take that 18 carbon long fatty acid and we add another double bond. Then we add another double bond. What happens to our melting point? Oh, it drops. So you've got a little bit of a trend there. As the number of carbons goes up, your melting point goes up. When you introduce a double bond, your melting point goes down. Now, the significance of that is your number of double bonds is going to take precedence in all of this. So, what I want you to recognize about this, however, is the top items right here. Now, the questions that I will ask you on your exam or quizzes or things like that, they're going to be focused primarily on these two trends: number of carbons in melting temperature and number of double bonds in melting temperature. I don't like to give you those. I like to kind of get to the point of, do you understand the trend, as opposed to, do you understand this very unique circumstance where there's a slight variation? Um, or layer something super deep where it's like, well, what about this one? You've added three double bonds, but it's two carbons long. What's the difference? Okay, so with that, I've got poll question. Boom, poll, polls. Okay, there we go. And yeah, we've got right off the bat. This is a little bit of a review one, but I want you guys to answer this. Dates back a little bit. And I'm actually going to jump ahead. Give another few seconds. The numbering system with the delta. So I've got my three different answers: carboxyl, methyl, or depends. Spoiler alert, it is not depends. And when it comes to the delta numbering scheme, I'm going to go ahead and stop my poll. I'll share the results. We had 73% of the class say that it was the carboxyl, and you guys are correct. The methyl end, that's your CH3, that relates to the omega or the N numbering scheme. So keep that kind of straightened out. Now, there we go. Okay. So that was our kind of discussion of fatty acids. Now, whenever we think about fatty acids, I always kind of think about fatty acids as like my base molecule. I use those to look at different lipids. Now, what I want you guys to remember here is this guy right here, glycerol. Have we talked about glycerol at all previously? We have. We talked about glycerol because we can use this to add to the chat, what is the three carbon molecule in glycolysis or gluconeogenesis that we can use? Close, close. What's G3P's best friend? DHAP. Absolutely. So we can take that glycerol and we can metabolize it to dihydroxyacetone phosphate, which we can use to make G3P, and then we can go on all the way to make glucose. Now, glycerol is our backbone molecule, and we can use that and esterify it. And when we esterify it, we can add a bunch of fatty acids to it. So where these OH groups are, we can add these acyl groups, and then we can add this long hydrocarbon chain. We can add fatty acids where each one of those hydroxide groups is. So we can add three fatty acids to it to make a triacylglycerol. Now, this right here is an example of a triacylglycerol. We've got three fatty acid side chains that are connected to glycerol or glycerol backbone with the help of an ester or an ester linkage. Now, most of these are going to contain two or three different types of fatty acid residues. So what that means is you're going to have fatty acids that differ in length, whether it's 16 or 18 carbons, and you're going to have differences in, are they unsaturated and it's 18 carbons long, or is it polyunsaturated and it's 16 carbons long? Now, when it comes to different fatty acids and triacylglycerols, I think that there's always a value to look at kind of a melting temperature of compounds and molecules. Olive oil at room temperature, chances are that's going to be a liquid. And olive oil is predominantly 16 and 18 carbon long fatty acids. Um, Beef fat by comparison, or bacon grease or something like that, chances are that's going to be a solid, and a hard solid at that, at room temperature. And what's that going to have a high percentage of? Well, it's going to have a high percentage of saturated fatty acids. So that's going to be a solid at room temperature. And the significance of this is your triacylglycerols and your fatty acids, there's a connection between how those exist and membranes that they're involved in. Now, triacylglycerols function as tremendous energy stores and energy reservoirs in animals. The fat content of normal humans allows them to survive starvation for 2 or 3 months. There was and sorry, I always like to bring this up. There's a guy whose last name, I forgot his first name again. His last name was Barbieri, and he is someone who fasted for a full 367 days. And in the process, he lost like, you know, 260 pounds or something like that. This is a gentleman who weighed, I would say, he was close to 600 pounds or something. Maybe it was 500 something, but he had a lot of weight, and he fasted for over a year and lost a ton of weight. Um, and this was done under the supervision of physicians, and he drank water and took vitamins every day. Um, that's not to say, oh yeah, you just take your vitamins and drink your water, and there you go. You don't have to eat ever. But what I like to bring this up because it's a way to stress the amount of fat that is available and the amount of energy that is available. Um, and so anytime you eat, like, I don't know, eat a piece of bacon or something like that, that has a lot of energy from it. And this is something that I have my kids, one of my kids, he's always asking about, he looks at nutrition labels and he'll look at the side and he'll be like, oh, Diet Dr. Pepper, this has 0 calories. And that's something that I'm always kind of, I'm sorry for sharing about my personal life, but it's something that I'm always like, I don't want him to have, like, I don't know how he picked that up. Was I looking at something and was like, oh, I don't want to eat that, because I don't want him to have a very negative experience with and a bad attitude about food and an unhealthy relationship with food, and to be like, oh, I can only eat this many calories. So I always try to like reframe it. My wife and I try to reframe it and say, well, calories are good because it's energy. And so anyway, my point is, like, fat is not bad. Okay. One of your classmates said, I found his name on Google. Angus. Dang, I wish that's such a great name. He fasted for 300 and oh, I was wrong. 382 days, and he lost 276 pounds. But wouldn't your overall energy be affected? Like, I go without eating all day. Even still feel fatigued, even with water. It's a great observation. And, I think that one of the factors at play is if I fasted long and I wasn't, okay, fair enough. I think one of the factors is that what's at play is, although your body is very responsive to energy inputs, I think that there's going to be a little bit of a lag. For example, if you just abruptly stop eating, and let's say that the last meal that you ate was pasta or something like that, your body's going to metabolize the sugars that make up that pasta. And then what's going to happen is your body's going to process through some of your glycogen stores. And at some point, you're going to basically start burning other fuel sources. And so, I mean, I'm a little bit speaking out of my nose on this. That's just my way of saying I don't exactly know what's happening, but I think that there's probably a little bit of a lag when your body transitions from this fuel source to this fuel source to this fuel source. Because, like I said, with triacylglycerols, you can get fatty acids and you can get that glycerol. That glycerol can be used to make glucose. And if your body is predominantly burning fats, well, that's fantastic. You're going to get a lot of energy out of that. Are you still going to be able to, kind of supplement and make glucose? Absolutely. Gluconeogenesis is taking place. How long does it take to be like fat adapted? If you do a Google search for fat adaptation on YouTube, don't worry. You're gonna find no shortage of people who have, oh, this is fat adaptation. Get your keto or what is your ketone strips from Walgreens, and you're going to see when you're in ketosis, and that's when you're burning nothing but fat. And I don't, I can't speak to the validity of that or anything of that nature. So sorry, lengthy response to a question there. But at any rate, triacylglycerols have huge amounts of energy available. Now, triacylglycerols also function to insulate. I always like to bring this up because can you add to the chat a Y if you have ever heard of olestra? I don't expect many Ys. Wonderful. I'm still at zero. I think I've asked that for like six straight semesters and nothing but no responses. Um, okay, thank you very much, Trinity. Olestra was a substance that was developed by Frito-Lay, and what it was a fat substitute. And it was a sugar-based or carbohydrate-based fat substitute. Um, and there were these chips that were Wow brand chips. They had wow and then an exclamation mark on them. And the idea was that you could make Doritos, but they were Wow Doritos, so their fat content was super low. But the great thing was when you bite into them, it tastes just like a regular Dorito. Oh, they were delightful. No, and everyone loved them for a little while. And then people had very, very violent, unpleasant gastrointestinal experiences related to Wow brand chips. And it wasn't so much, I don't think that there was anything that was like long-term hazards. It was just like people would go into the grocery store and they'd be like, "Oh, I gotta get some chips." And then someone would be like, "Oh, you should get some Wow chips." And the response would be like, "Not this time. I've had them before. I think I'll move forward." And so, yeah. Um, so they were, at any rate, they were popular for like the summer of 1997, and then it kind of went downhill. Okay. Now, here we go. If you've ever read the book Fight Club or watched the movie Fight Club, they talk about this industrial process, saponification, and that's the industrial process by which you can make soap from triacylglycerols. Use aqueous sodium hydroxide, mix that with your triacylglycerols, you're going to get glycerol, and you're going to get sodium salts of fatty acids. Those sodium salts are really great for basically washing your hands and such. Um, the enzymatic process, what's taking place in your bodies, is catalyzed by these molecules or enzymes known as lipases. Lipases will take a triacylglycerol, give you a glycerol backbone and ionized fatty acids, releasing those individual ionized fatty acids. Okay, so triacylglycerols have a huge energy store, or they are tremendous energy stores. They're glycerol plus fatty acid, or multiple fatty acids. Now, lipids can also fall into a couple of different categories. A triacylglycerol, that is an example of a nonpolar lipid. They are a great energy store. Glycerophospholipids and sphingolipids, depicted here, are examples of polar lipids. Now, these polar lipids are basically the basis for your lipid bilayers. A glycerophospholipid. What I want you to recognize about a glycerophospholipid is the glycerol backbone. Now, in addition to a glycerol backbone, which I'm going to highlight and circle right here, so in this R1 position and the R2 position under model B, you have fatty acid chains, Fa. I'll label that there, Fa. So you're going to have these 16 or 18 carbon long fatty acids. Then you'd have a phosphate group, hence the glycerophospho. That phosphate group is going to have a negative charge to it, which is where your polarity is going to come from. And then off of that glycerol phospholipid is an X or an X head group. Glycerophospholipids are major lipid components of biological membranes. So anytime you talk about a lipid bilayer, I think it's fairly common to talk about the nonpolar tails and the polar head group. This glycerophospholipid is where we're getting that polar head group terminology from. That X that is partially obscured is where we've got some variation. A glycerophospholipid is, and this is a new term, or maybe a new term for you, is a amphiphilic molecule. That means that it has a polar and a nonpolar end. You might also see this as a hydrophobic and a hydrophilic end. So amphiphilic means that it's got a nonpolar and a polar region, or a hydrophobic and a hydrophilic region. Now, these X, or these phosphoryl X head groups, are really significant. Here, what we have are examples of these different X head groups. So this, what I've circled, or I'm putting a box around right now, is this whole thing. Okay. I'm sorry, I made a mistake. Yeah, plus the phosphate group. X is where we've got variation. Now, I want to highlight one specific model because I think that will be helpful whenever it comes to the activities that are posted, that I will link on our homepage, but are up right now. This X is where something can vary. Okay, now I want to draw your attention to this molecule right here, phosphatidylserine. This is the name of a phospholipid. Now, phosphatidylserine, does any part of that name sound super familiar? Perhaps related to amino acids? Serine, you're absolutely right. Now, if you're thinking about serine, which I am, I mean, am I thinking about serine every day? Nearly. Whenever I think about serine, here's how I draw it. That's how I draw my backbone, and then I draw serine, CH2, OH. Now, when you look at this formula for the X, your X in this case is serine. Now, this right here, that is the amino acid serine. Now, translating a singular line to a structure, I think is a little bit challenging. But what I want to draw your attention to is I'm going to change colors for this because I'm going to highlight or circle different things. This group right here is those atoms right there. This group right here is those atoms right there. That means that this is my alpha carbon. That means that this is that hydrogen. And then that means that this CH2 is a part of my R group. So when I look at this formula for X, what is omitted compared to this structure right here? Add to the chat if you recognize what's omitted. OH, you're absolutely right. Now, the tricky thing about this is it really omitted? Yes and no. It's omitted, but it's also kind of not because this phosphate basically replaces that OH. So that's our linkage that brings us back to our glycerol to give us phosphatidylserine. Now, with that in mind, if I were to ask you, say, on a homework or an activity, ask you about phosphatidylthreonine or phosphatidyltyrosine, you're kind of drawing the same thing, but you're replacing that OH group with basically this whole thing. Now, I bring these up because what did I say? What did we say here? That these are the major components of biological membranes. So that means that whenever we draw a membrane, and we draw, I always draw a lipid bilayer kind of like this. Two tails, and then, oh yeah, that's my polar head group. Well, It's this whole thing right here. Well, sorry, this whole thing right here. I'm drawing a line on a line on a line, so I apologize. It's this whole thing right here, which is the same as this right here, that is that head group right there that gives us that polarity. Now, like I said, some of these head groups are super large, some of them are small. Some of them, if we look down here, phosphatidylglycerol. What? That is bananas. This whole thing where I'm drawing an X replaces this X right here. So these head groups can be massive. Now, what's the significance of these head groups? Well, the presence of these head groups is a way of communicating. Now, sometimes those head groups are to send a message basically outward. For example, some of those head groups will say, "Oh, well, this cell is stressed. X, Y, and Z is happening within this cell. Therefore, phosphatidylserine will go from the inside of the membrane to the outside of the membrane." That's kind of like a, communicating distress from that cell. And so then all the adjacent cells will be like, "Oh, okay, well, we got to respond in turn." So these are glycerol phospholipids. Okay, it's 7:36. We've spent a lot of time on fatty acids, triacylglycerols, and glycerophospholipids. We have a total of two more things that we need to talk about: sphingolipids and steroids. With that in mind, though, if the king's ransom of what we've spent time on in classes, those three things are going to be kind of the more important things that will be tested over. That's not to say the rest of this will not be, but those are the big money items, in part because when you go on to take metabolism and later this semester, when we talk about beta oxidation, we're going to be going back to, well, let's take a triacylglycerol and break it down. Then let's take a fatty acid and break it down and get energy from it. So those are things that you dig a bit more deeply into. And glycerophospholipids, same sort of thing. You use those to talk about communication, how this cell says this to this cell. Okay. Now, sphingolipids, one of our last two items. Sphingolipids are major membrane components. They are derivatives of an 18 carbon amino alcohol known as sphingosine, right here. Okay. An 18 carbon long amino alcohol. Okay, so let's see. One carbon, 12, that gives us 13, 14, 15, 16, 17, 18. So one of the things that I like to look at these fatty acids, or sorry, I like to look at these lipids in the same way that I look at glycerol, because I look at it and say, this is very similar to my glycerol backbone. So whenever I think of a sphingolipid, I think of sphingosine. And then, where's my amino group? Well, it's on this carbon right here. Whenever I'm talking about a sphingolipid, our base molecule is known as a ceramide. And a ceramide is sphingosine with a fatty acid residue. So where that amino group is, this NH3, that's where I'm going to put a fatty acid onto it. So our base unit is a ceramide. Now, this R group, that can vary. It can be 12 carbons, it could be 16, it could be 18, it could be 24 carbons long. Those are different sphingolipids. So these terms sphingolipid and ceramide, they seem a little bit interchangeable. Sphingolipids, the big umbrella. Ceramide is an umbrella that's almost like completely underneath sphingolipid, because those fatty acid residues, there are many different fatty acid residues that can be plugged in there. Now, sphingolipids that are important, specific sphingolipids that are important, are sphingomyelins and cerebrosides. Sphingomyelins have the head group of phosphocholine or phosphoethanolamine. Okay, now I'm going to jump back a second because I want you to look at those. So These head groups, ethanolamine and choline, those head groups, whether it's this one or this one, can be tacked onto a um, a ceramide to make either one of these specific sphingomyelins. Cerebrosides have a head group that has a single sugar such as glucose or galactose. So what I want you to take away from our this introduction to sphingolipids is that there are two major types of sphingolipids, sphingomyelins and cerebrosides. They are membrane components and they are building blocks for kind of communication. And what do they look like chemically? Well, the head groups are significant. And the head groups are significant because they say kind of what they do. So, what I'd like you to take away from this is I'd like you to know what a sphingolipid's backbone looks like, that being this right here, that 18 carbon long backbone. And then we can put a head group on and we can put a different fatty acid group on. Those are the things that I want you to know about a sphingolipid. I want you to be able to look at a molecule and discern, is this a sphingolipid? Is this a glycerophospholipid? Is this a triacylglycerol? Those are things that I think are valuable and important for you to be able to do. Now, phospholipases. Phospholipases are enzymes that are involved in processing of glycerophospholipids as well as, well, just different lipids. Phospholipases are responsible for the continuous degradation of membrane phospholipids and sphingolipids. What I want you to focus in on, and there's a question in one of your activities that asks you about phospholipase C and D. Do they cut in the exact same location on a phospholipid? They do not. One of them, phospholipase C, will cleave off the phosphate plus the X head group. Phospholipase D will just clip off the X head group. You got a question about that. What I want you guys to know about these is, well, what do phospholipases A, C, and D do? I'll give you a little bit of a phospholipases A and C, what they are going to do is they are going to effectively do the same thing, but just at a different location. They're both going to release a fatty acid chain. Okay, now know where these lipases cut. Okay, so at this point in time, we started with fatty acids. Those were energy stores. We learned about the structure of them, the terminology associated with them. Then we looked at triacylglycerols, which are, I would say, as close to a polymer of a fatty acid that you're going to find, but they're really just molecules that have three fatty acid tails. Then we talked about glycerophospholipids and sphingolipids, as well as phospholipases, the enzymes that are responsible for processing them. All of those different molecules, those were our first four classes of lipids. Those all have a membrane component to them. They are either involved in a part of a molecule that makes a membrane, or they are involved in making up a membrane. Now, there are also lipids that have non-membrane functions. They are signaling lipids, lipid cofactors, and pigments or antioxidants. Now, signaling lipids, there's one group known as eicosanoids. They mediate inflammation, fever and pain responses. Steroid hormones act as chemical messengers. Lipid cofactors, for example, ubiquinone, is involved in the electron transport chain and serves as an electron carrier. And then there's also pigment molecules. If you've ever seen, or an example of this would be beta carotene. That's a pigment molecule. That is also a lipid. Now, I think what I'd like to do is I'd like to go ahead and take a pause and actually, I think what I'm going to do is stop right here for the day. Um, and what I'd like to do is open the floor for anyone who has any questions. And I'll post up the last poll question. Um, but if you have any questions, go ahead and ask them. I just want to carve out a little bit of time. I can stop my recording.